Hi, everybody. This is our first in our online lectures, our video lectures that I'm going to post, going through each section until we hopefully come back and are meeting together again in person. So I hope you guys are doing well, you're staying safe, and you're all healthy, and that you're ready to learn here online. We'll see how this goes. My plan is to post these and then we can chat about them in the live meetings. Maybe your schedule has changed, your work and other responsibilities. Who knows what? You'll at least get to watch these videos whenever you get a chance. I'm going to break each section down into small chunks. So we'll see exactly how long, but I'm thinking maybe something like 12, 15 minutes pieces. And towards the end of some of those pieces, I'm going to give you one to work on. And then when we come back at the next one, then we'll go through it together, kind of like if we were in class. And then, yeah, any questions, bring those to the live sessions at our normal class meeting on Zoom. And I provided all that for you guys. So just want to say hi, since this is our first meeting here before we get into our section. Hey, how are you? I'm here in my office still. This is actually last week for you guys by the time you watch this. They still let me in to the campus this week. By the time you watch it, I'll have figured out a new location to film these from. But okay, anyway. So what's going on? So we're in 3.6. We just learned about implicit differentiation in 3.5, which was based on the chain rule, which was 3.4. So it's all building up in this strategic way. So the idea here, we've got applications. These are going to be word problems that build on the idea of implicit differentiation. This is really the first true applications that we've seen of derivatives. So pretty exciting, also kind of intimidating for sure, but we've built up to this slowly. So let's go for it. First, a quick recap of implicit differentiation. Take the derivative of both sides with respect to x. So when we started that conversation, we began with this: x squared plus y squared equals 25. I said, okay, if we try and take the derivative of both sides of this implicit equation, then I might write something like that: d over dx to the left side, d over dx of the right side. And then when I take those derivatives, here's how it would play out, right? So we did this right before. So the derivative of our x is the typical, with respect to x. But the y, taking the derivative of y with respect to x, we say, okay, well, I'll do it like normal to y, but then I've got to multiply by dy over dx because of the chain rule happening. And we had that whole conversation when we were still meeting together. And then, of course, the right side, that derivative is 0. Okay, so we're going to take it up a level. Now the question is, still working to introduce this idea of related rates. Take the derivative of both sides with respect to t, not with respect to x. So maybe the first thing I'd write, if it's with respect to t, is d over dt. d over dt for the left and the right. And now, okay, we've taken it up one level further because now neither of these are at t. So when I take the derivative of x, it's going to work in a similar way as the y. And here it is. The derivative of my x squared is 2x. But now because it's with respect to t, I have to multiply by dx over dt. And then the y is similar to y, but then I'll multiply that by dy over dt. And so both of them, we've got this chain rule happening. Okay, you can see that. And then the derivative of the right is still a 0. What is going on here? This is where we get the name for the section. Now we have an equation that involves two different derivatives, one with x, one with y. And we know that derivatives, they represent an instantaneous rate of change. They represent a rate. How fast is something changing, right? Like miles per hour, right? What's the change? So since we have two of them, they're related in an equation. Those are literally related rates. And okay, that's where the name of this section comes from. Now, let me kind of take this a step further, because the word problems that we're going to do, we're going to have to find a derivative of this nature, but then we're going to have to go a little bit further. What if I asked, hey, based on this statement right there, what is the value of dy over dt when x equals 3, y equals 1, and dx over dt equals a half? I'm just making up some numbers just so we can see how this will play out. What's the value of dy over dt when I'm told the value of x, the value of y, and the value of dx over dt? And well, it's nothing too crazy. I mean, it looks kind of intimidating, but all we're going to do is plug those numbers in. If x is 3, then I'm going to plug in 3. If dx over dt is a half, then I'm going to plug in a half. Plus 2 if y is 1. All right, and we're looking for that value. And so what we'll do, and I'll kind of like try to transition pages here, we can simplify that, right? 3 plus 2 dy over dt. If I solve, dy over dt equals negative 3 over 2. So once I have my related rates equation, then we're going to be able to figure out values of the other pieces, or of some of the pieces, and figure out, maybe the value of the unknown in this case. Okay, hopefully you're able to follow along so far. Of course, if not, obviously you guys know how to use videos. Stop and pause and go back if you need to, because it's difficult for me when to know I'm going too fast or too slow when I'm just talking to myself here. Okay, so next up, we've got this word problem. So I'm going to read it. I'm going to give you guys a moment to write that. And we're going to pause. We're going to stop the video after I read this one. I'm going to let you try it out on your own. Then we're going to do it together when we start the next one. But here it is. A rock is thrown into a pond, creating a circular ripple. So you can probably picture that. You throw a rock into water, it makes a circle that gets bigger and bigger. If the radius of the ripple increases at 5 feet per second, how fast is the area of the circle changing when the radius is 20 feet? Okay, so we throw this rock into the water. It creates a ripple. The radius of the ripple is expanding, is increasing at 5 feet per second. So how fast is the area of that circle changing or increasing when the radius is exactly 20 feet? I'm going to give you a hint before I let you go. Well, we're going to need to start with the equation for the area of a circle. They mention area, they mention the radius. There's your hint. Area equals pi r squared. What you'll need to do, take derivatives with respect to t, plug in the values that you know, and try and answer the derivative that they're asking about. I'm going to pause it right here. I'll give you a moment to maybe pause the screen and take a look at this one on your own. Good luck. I'll see you at the next video.